Hello everyone. Let's begin with a simple comparison. You know, when we connect a capacitor to a battery, it charges once and then the current stops. That's exactly what happens in a DC circuit. The current dies down as soon as the capacitor is fully charged. But in an AC circuit, things are very different. The alternating source keeps reversing polarity, so the capacitor is charged and discharged every half cycle. That means current flows continuously. Mathematically, the source voltage is V of t equals Vm sin omega t. So, unlike DC, AC ensures that the capacitor never settles. It keeps the current alive through repeated charging and discharging. Students, we've seen how inductors make current lag. Now let's discover the opposite behavior, what happens in a capacitor. We begin with the charge on the capacitor at time t. Q equals C multiplied by V of t, which is C multiplied by Vm sin omega t. So, the charge is directly proportional to the applied voltage. Now, current is defined as the rate of change of charge. That means I equals dq by dt, which comes out to Cvm omega cosine omega t. But here's the interesting part. Using the trigonometric identity, cosine omega t is equal to sine omega t plus 90 degrees. So the current becomes I of t equals Im sine omega t plus 90 degrees, where the current amplitude Im equals omega Cvm. And this tells us something remarkable. In a capacitor, current leads voltage by 90 degrees, a perfect quarter cycle ahead. Quick insight: capacitors don't wait for the voltage to rise. They immediately draw current to start charging or discharging, which is why in a pure capacitor, current always runs ahead of the voltage wave. Now that we've derived current in a capacitor, let's see how capacitors oppose alternating current. We define this opposition as capacitive reactance, written as Xc equals 1 divided by omega c. Here, omega is the angular frequency of the source and c is the capacitance of the capacitor. Notice that the unit of Xc is ohm, the same as resistance. But unlike resistance, which is constant, capacitive reactance depends on frequency. The amplitude of current is expressed as Im equals Vm divided by Xc. That means the smaller the reactance, the larger the current. And here's the key insight: if the capacitance is large or if the frequency is high, the reactance becomes very small. As a result, the capacitor allows more current to pass through. So, quick takeaway: capacitors actually allow alternating current to flow more easily at higher frequencies. That's why they are widely used in filters, tuning circuits, and high-frequency applications. Students, here comes one of the most striking results in AC circuits. In a capacitor, current always leads voltage by 90 degrees. Let's first look at the Phasor diagram. The current Phasor I is ahead of the voltage Phasor V by exactly 90 degrees. That's a quarter cycle lead. Now compare the time graphs. You can see that the current wave I of t reaches its peak 1/4 cycle earlier than the voltage wave V of t. This is the complete opposite of what happens in an inductor, where current lags by 90 degrees. This behavior makes the capacitor a phase-advancing element. It doesn't wait for voltage to rise fully. The current jumps ahead, charging and discharging the plates before the voltage hits its maximum. Quick insight: in a capacitor, current always stays one step ahead of voltage exactly by 1/4 of a cycle. This property is crucial in timing circuits, oscillators, and power factor correction in electrical systems. Students, we already saw how inductors do not consume net power. Now let's ask, does a capacitor consume power? Let's begin with the expression for instantaneous power. Power is voltage multiplied by current. Substituting, we get Pc of t equals Vm sine omega t multiplied by Im cosine omega t. When simplified, this becomes Pc of t equals 1 by 2 Vm Im sine 2 omega t. Now observe this carefully. The value of instantaneous power swings equally positive and negative over time. That means during one part of the cycle, the capacitor is absorbing energy, and in the next part, it is returning that energy back to the source. If we take the average over a full cycle, the result is 0. This proves that an ideal capacitor, like an inductor, does not dissipate energy. Instead, it simply stores energy in its electric field and then releases it again. Quick insight: pure capacitors, just like inductors, consume no net power. They behave as energy storage devices, temporarily holding energy but never wasting it as heat.
Now students, let's put our capacitor concepts into practice with a real example. We are given a capacitor of 15 microfarad connected to an AC supply of 220 volts at a frequency of 50 Hz. Let's calculate its reactance and the current flowing. Step 1. Reactance. Xc equals 1 divided by 2 pi Fc. Substituting 1 divided by 2 pi multiplied by 50 multiplied by 15 into 10 to the power minus 6. This comes out to roughly 212 ohms. Step 2. RMS current. I equals V divided by Xc. So 220 divided by 212. That gives about 1.04 amperes. Step 3. Peak current. Im equals root 2 multiplied by I. Substituting, root 2 multiplied by 1.04, which comes out close to 1.47 amperes. Step 4. Effective frequency. If we double the frequency, the reactance Xc will become half, and that means the current will double. So the result is reactance equals 212 ohms, RMS current equals 1.04 amperes, and peak current equals 1.47 amperes. Quick insight: this clearly shows that capacitors allow AC current more easily at higher frequencies, exactly as theory predicted. So, let's bring it all together. In an AC circuit, a capacitor is never at rest. It keeps charging and discharging, allowing current to flow. The current always leads the voltage by 90 degrees. The capacitive reactance, 1 over omega c, controls how much current flows, and this reactance decreases as frequency increases. Like inductors, capacitors don't consume average power. Instead, they store and release energy in their electric field. I hope this session gave you clarity on capacitors in AC circuits. In our next discussion, we'll combine resistors, inductors, and capacitors in a series LCR circuit. And that's where things get truly fascinating. See you then.